Hi folks, today we're going to talk about a very special function called the impulse response. Actually, it's not a function, it's more a characteristic of a linear time-invariant system. And it completely characterizes a linear time-invariant system, which is an amazing thing. If you remember up till now, we've been talking about systems, and we talk about, an input, say x of n, and then we have a system, and then we have an output y of n. And we've talked about the input-output relationship between the input and the output, right? We've said y of n is equal to twice x of n, y of n is equal to e to the power x of n, or something like that. But we've kind of been restricted to very simple characterizations. What we're going to do now is we're going to come up with a way where we don't need to explicitly write down the input-output relationship, and the system in its entirety is characterized by one response of a system. And that response is the response of the system to an impulse. This is kind of weird, but it works. But it only works for linear time-invariant systems. So we will kind of stick to just linear time-invariant systems in this class. So we have an input, say, which is an impulse, delta of n. Then the output is the response to that delta of n. And because it's such a special response, we give it a special symbol, and we represent that by h of n. Now this input is an impulse, right? So the output is the response of the system to an impulse. And because it is the response of the system to an impulse, it is called the impulse response. Engineers are pretty straightforward people. I mean, all our nomenclature is kind of like that. It's very, very simple, right? But do remember this, because one of the ways I'm going to kind of make sure that you remember this is I'm going to give you things like, I'll give you an input-output relationship, and I'll say, what is the impulse response? And you can find that really, really easily by taking the input and then replacing it with an impulse function, a delta function, right? So now we're just doing this for a discrete time system because it's easier to see, and then we'll go ahead and we'll do this for a continuous time system as well. Okay, and here's the amazing thing. This response is the response only to one input, and the input is a delta function. And remember what the delta function in discrete time is. It's just 1 at n equals 0 and 0 everywhere else. And the fact is that if I know the response of this discrete linear time-invariant system to this one input, I completely know what the system is. I can characterize that system completely. I can tell you what the output of the system is going to be for any given input. I can tell you if the system is causal, whether it's memoryless, whether it's stable. All of that information is contained in this one little thing, the impulse response. Okay. To see at least the input-output thing, let's take a very simple input and see how that works. So let's suppose I have x of n, which is, say, 1 for n equals minus 1, and 2 for n equals 0, and 1 for n equals 2, and just to keep the writing small, keep not having to write so much, let's say 0 otherwise, right? So if you think about it, what it looks like is here is 0, here is minus 1, so it's 1 for n equals minus 1, and it's 2 for n equals 0, and it's 0 for n equals 1, and it's 1 for n equals 2, right? So this is what x of n looks like. Okay? Now, I could write this thing here is just the delta function shifted over by 1. So this thing here is just delta of n plus 1. Remember that this is delta of n. This here then is 2 times delta of n. And this here is delta of n minus 2, right? So this is this delta function shifted to the left by 1, so we write that as delta of n plus 1. This thing here is just twice the delta function. We don't have anything over here, we don't have to write anything. And this thing over here is just a delta function shifted to the right by 2, right? So I have the whole thing, x of n, I can write as that. And we did this when we talked about the delta function. We showed how we can take an arbitrary x of n and write it in terms of the delta function. And if you remember, we said that in general then I can take x of n and I can write it as summation from k equals minus infinity to infinity x of k delta of n minus k. Right, so here x of k is 0 except when k is equal to minus 1, and when k is equal to 0, and when k is equal to 2. So x of k is 0 except for these 3 locations. And so this one, I could have written this as x evaluated at minus 1 times delta of n plus 1 plus x evaluated at 0 times delta of n plus x evaluated at 2 times delta of n minus 2. And that's what I have over here. Okay, this is what we're going to use. Important, right? Okay, so let's take our system. And again, here is our system. And let's put into it say delta of n, right? Then the output we know by definition is h of n. Now, if instead of delta of n, we put in delta of n minus k, by time invariance, I shifted delta by k units, so the output will get shifted by k units. So if I put in delta of n minus k, this becomes h of n minus k, right? So I can write it like this. I can say delta of n minus k, and the output will become h of n minus k. Okay, so this is the input, this is the output. I could take delta of n minus k and I could multiply that with x of k. Then by the scaling property of linearity, remember, if I put a gain on the input, I get the same gain on the output. So this will become x of k h of n minus k. And now I can take the sum of this from k equals minus infinity to infinity. And remember, in a linear system, if I take the sum of the inputs, the output is just the sum of the corresponding outputs, right? So this will become summation x of k h of n minus k. Right? So k equals minus infinity to infinity. But this, we already said up here, we said x of k delta of n minus k, k equals minus infinity to infinity, is just x of n. Okay, so what we're saying is the input to the system is this arbitrary x of n. That means this must be the output y of n. Okay, so we have, and let's write it out explicitly, y of n is equal to summation x of k h of n minus k. We can forget about the system now. Whatever the system was is not important. What is important, only important, is what the impulse response was. Because knowing what the impulse response is, now you can give me any arbitrary input and I can tell you what the output is. All I need to know is the impulse response. And I can take shifted versions of the impulse response, weighted by the input, and I get the output. That's a cool thing. Okay, so this is called the convolution summation. Unfortunately, in practice, what you'll find is that evaluating the convolution sum is a pain, and it's a pain that you will be subjected to for a little bit anyway, at least until the first test. And the reason for that is that you need to get a feel for the system. That's one thing. And the other thing is that if I don't teach you this, then the people who teach you the courses after 304 come back and yell at me. So you will need to know how to evaluate this, and we'll spend a module on figuring out how to do a convolution sum, and I'll try and give you enough different examples that it shouldn't be too difficult. I'll also show you in the notes, you'll be able to see that this thing here, this summation here, can be also written in this way. I can take x of k, h of n minus k, k going from minus infinity to infinity, and I can also write that as summation k going from minus infinity to infinity of x of n minus k h of k. And you can show this really easily through basically variable substitution, and I'll show you that in the notes, because it's just tedious. I mean, there's nothing really very difficult about it. It's just a bit tedious to go through, so I'll just leave that to the notes. Okay, so this is for a discrete time-invariant system. If I have a discrete linear time-invariant system and I know the impulse response of the system, and remember what the impulse response is. The impulse response is simply the response of the system to an impulse. If I know that, then I know everything there is to know about the system. Okay, what about a continuous system? As long as if I have a continuous linear time-invariant system, how does that work? Well, it works in exactly the same way. So again, here's my system. If I take the input and set that equal to a delta function, then the output will be the response to that delta function, or the response to that impulse function, or the impulse response. And again, we'll denote that with h, right? And we'll get the input-output relationship of a linear time-invariant system using the impulse response in exactly the same way that we did with the discrete time system. So if you go back, when we talked about the impulse function, we had said that we can write x of t, any arbitrary x of t, is minus infinity to infinity x of tau delta of t minus tau d tau. This is called the shifting property of the delta function. So this is what we're going to use in order to develop the input-output relationship of a linear time-invariant system using the impulse response. So we'll go through the same steps again. If I have an input delta of t, then the output is the impulse response h of t. So if the system input is an impulse, the output is the impulse response. I can take that input and shift it. And if I shift it, then the output gets shifted as well. right? That's time invariance. Time invariance says that if a system is time invariant, if I shift the input, the output gets shifted. And finally, I take this and use the scaling property of linearity, which says if I multiply the input by something, then I have to multiply the output by the same thing. Okay, and finally, I use, again, the property of a linear system, which is if I take a sum of inputs, then the output is going to be the sum of the corresponding outputs. But because this is continuous time, instead of a sum, I'm going to take an integral. So if I take the integral from minus infinity to infinity of x of tau, delta of t minus tau, d tau, then that gives me an output of minus infinity to infinity of x of tau, h of t minus tau, d tau. Right? And this, as we said earlier, is just the input, any generic input x of t. So this is a generic output y of t. And y of t then I can write for a linear time invariant system. If I know its impulse response, I know everything there is to know about that system. Okay, I can tell you everything there is to know about that system, and I can get the input-output relationship using this integral. And this is called, as you may guess, the convolution integral. And as in the case of the discrete time, I can take this and do a variable substitution and convert this integral into this. The reason why I'm showing you both these forms is when you are actually trying to compute the convolution integral, sometimes you'll find it more convenient to use this method, this integral, and sometimes it'll be more convenient to use this integral. Neither one is better than the other. It's just a matter of which one is more convenient to use. Okay, so what do we have? We have the response of the system to an impulse tells you everything you need to know about a linear time invariant system. Okay, so all you have to do, if I have a linear time invariant system and this particular system is neither linear nor time invariant, but if it was, then if I gave it an impulse, which in this case would just be a tap, then that response would tell me everything there is to know about this particular system. I could assume that it was linear, and it would still, you get some information about it, and people do that. In one particular application, which is when you're, say, prospecting for oil and you want to know what the subsurface, the geologic formation in the earth look like, one way you figure out what that particular system is, that system being the earth itself around that area, is you dig a hole, I think it's about several meters deep. I seem to remember 6 meters, but that I might be off on that. But you dig a deep hole and you fill it with dynamite, and then you light the dynamite. And that explosion is an impulse. And what you do is you surround that area where, a little far away, but not too far away, that area with geophones, which basically measure the vibration of the surface of the earth. And you measure the vibration of the surface of the earth, and that becomes a two-dimensional impulse response to the system. And you look at that impulse response, if you're a geophysical engineer, and you try to figure out whether it's worth digging a well to see if there's any oil there. Because well digging is very, very, very expensive. And so you use various systems to increase the chances that when you dig a well, you'll strike oil. Okay, so that's one particular impulse response. There are all kinds of systems where we'll look at a few, where we'll look at the impulse response. Given the impulse response, we'll be able to tell everything there is to know about the system, as long as we can assume that the system is linear and time invariant. Okay. Unfortunately, on our way there, we have to do a lot of convolution. And like I said, that's going to be a pain, but it's going to be a pain you're going to have to suffer anyways. You might as well do it. And so I'll give you all kinds of examples and things to work, and hopefully you'll get really, really proficient on it, and people will say, who did you take signals and systems with? Or maybe not.